People always think we're attacking NASA, and we're actually NASA enthusiasts when it comes right down to it, right? We're space enthusiasts. We want accountability. We want disclosure. We want to see what's actually there, and we will accept the limitation. We'll support the limitations on what's capable of doing. We don't need to keep researching in and find out, oh, all we're looking at is CGI. If you can't do it, say so.
If you wanted the other guy to understand, we could go by the definition. What does it mean to have some force hitting against the wall? I think we described it in the first series of the videos, where we had the atoms whizzing around within something. That something will be bloated. If there is no atoms outside trying to push it back in, it will expand. Generally, when you are trying to describe an example, when you put more things in, it's worse for the other one to understand, yeah? Your explanation was for university. It was not for someone that cannot grasp early point ideas. Your explanation was for someone that is entering the university to understand what are the principles in matter states and how you keep something pressurized in liquid and all that.
Yeah, and the thing is that force is trying to pull that zipper apart. Let's say we just take a sheet of material, put a zipper in between it, and set 4 cars on top of it.
That's the amount of light that they are saying. But I love the way that you compared the two suits. That it shows that if you are to deal with these insane forces, you have to have some structure. First thing that the professor said at the university is that LEM with 1 millimeter of aluminum being that big, with 1/3 of the atmosphere inside, it should blow up like a whatever. It was laughing.
People simply don't understand it. We're even showing images of your vacuum chamber, and you can see the thickness of the walls. This was a physics professor, by the way, from a university in the United States, and he's going, well, I put 65 pounds of pressure in my bicycle, and that's not a problem. I can pump my bicycle tires on my bicycle, pump up to 65 psi. What's the problem?
It depends on the bloody area. If you use the walls of that tire, if you had a much bigger tire, try putting to whatever psi in there. And especially when you have atmosphere outside, yeah? We're not talking about vacuum outside and the pressure inside a bloody elastic. He must be crazy not to understand that that thing gets linearly raised as the area raises. As the area gets bigger, you get more force. It's bloody insane if you're a professor.
He claimed that on the thing. He said, oh, and I worked with vacuum chambers and everything else when I was in university, just taking my stuff. I just said, well, we just put 2 psi in a bicycle tube, put it in a vacuum chamber, and it literally just expanded until it filled the entire chamber.
Or if it's not flexible enough because some cloth inside, it will raise so much force that it will just explode. It will bulk up until the cloth cannot handle it anymore, and it will break apart.
Robert has in one of the videos, because he captured the new inflatable pods to go on the ISS, and he has a test of it. You know, the lifting straps that they lift boats with and stuff, like heavy lifting straps that are 5 and 10 tons a piece. Mm-hmm. This thing is an entire weave of these straps on it. They put 192 psi in it, and it was chained down on these big steel, like gigantic chains and everything else, and there was about 8 of them on there. And when it blew, it took the entire frame and pushed it out through the side of the building. This is what people go back to. They read a piece of a document, and they come up with a little line like this, and this is what I clipped out. This is in any of the NASA documents, right? And it just says 100% vacuum means that there's no particles present, so there's 0 pressure.
If you have an area with 0 pressure and the outside area is 1 atmosphere of pressure, you get the force. If it was 0 atoms inside and 0 atoms outside, you would not get any force. The pressure is 0 that it is exerting, the vacuum of 0. But outside the vacuum, outside the walls, the pressure is 1 atmosphere. You are not getting any force from the inside. From the inside to the outside, the force is 0. And from the outside to the inside, the force is, how many tons per square centimeter. So you get the full force because you have no force from the inside and the full to counteract, and the full force from outside.
Exactly.
You get force when you get atoms, because the atoms are those that bounce on the bloody wall.
That makes sense. Here's another document that I pulled up. This is the specifications of a differential vacuum gauge. So all you have to read is the bottom line.
Warning, exceeding the maximum pressure range will destroy the sensor, of course, yes.
When you look at the specifications of these sensors, like that's a differential sensor, right? These are new models of the thing. This one was designed to go to -6 or whatever. Basically, the little sensor in that gauge is exactly like a McLeod gauge, which is the very first vacuum gauge created. And it's a 2-stage liquid mercury in little tubes to be able to read and push on that thing. And people don't think that vacuum is a force. Because it doesn't have a force, the other force is now acting.
When you have a vacuum and you have something that is acting upon the walls, from the vacuum nothing pushing back, you have everything pushing against for that to collapse.
When you're doing a calculation and it shows negative, and you have a negative torr, right? And everybody says, well, you can't have a negative force.
Of course you can, it's pointing the other direction.
It's just pointing in the opposite direction that is pushing against the... You create a wall, and you're pushing it one direction or the other direction.
Exactly.
So you have a positive force or a negative force.
It depends from where you measure it. If you are measuring from inside, you'll see a pressure coming to you. If you're measuring it from outside, you'll see a pressure going in. So it depends of the viewer, of course. That's all it is, having a negative pressure. I think people will get it the way that it's being described.
There are a few that just argue for no apparent reason, but the ones that really don't get it, that want to make comments, I mean, when they sit there and say, well, I got a physics degree.
He may be as well using another one's name.
And that's exactly could happen as well, right? On a couple of occasions, I had people that work for NASA contacting me. One was the son of a space shuttle astronaut. And he said, well, my father never said anything before he died, right? He was actually questioning it. Like, how can they be running around outside if you claim this vacuum is this much? And I said, well, you do the calculations. You happen to be in a position where you can ask the other astronauts what's real and what isn't.
If they're worried about their families and their lives, what can they say? They cannot even say anything, especially within any headquarters, because you never know whether microphones or cameras may pick you up. You don't even trust your brother there.
Yeah, well, like I said, if his father didn't disclose anything, it's because he's keeping the secret as well. I looked up Felix and Paul Studios, which are associated with NASA. And we have all the links. You can go to the movie studio. There are all the simulators for the ISS. 2D, 3D images. They're showing all their fancy cameras off. They actually put the cameras up on a satellite or something, or they actually, whatever's floating around there for the ISS, they're actually doing some filming there. Then they bring it back down on a thing. They have a studio for inside the ISS and another studio for outside the ISS. I mean, why do you need a film studio? It's not a training facility. The ISS is built on tubular forms that are 15-foot in diameter, all of the tubes. You see all of the images of them. They're not in 15-foot diameters. You can see they got a window in the floor and a window in the ceiling, right? It might be 8 or 9 feet. Well, take a look at the Felix and Paul Studios, right? They don't have 15 feet. They built the pods in there, and they've got an open up front end for the movie studio guys to go in there and film. It's absolutely crazy.
We had the vacuum chamber out of service, not the main one, but we were trying to make a secondary one, because we didn't want to contaminate the primary one. And because it was left alone, doing nothing, we had 1 week of trouble assembling it and reaching, the 10 to the -6 we wanted. Those plastic rings, the O-rings, can actually get you down to 10 to the minus 6. It's very hard. After 10 to the minus 6, you do need those metal gaskets. 10 to the minus 6, 10 to the minus 4, then to the minus 6, depending on the gasket. If it's high quality, you can get down to the minus 6. So, because our chamber was out of service for 1 year, we had to go through all the bloody gaskets. I've seen, Robert, the video where one was so old that it had cracked. I have to also send you a last batch of videos, and I'm also waiting for the films to be developed here. What we saw was, we never expected so much outgassing, and it actually fogged a bit in the window. Before it outgasses, the window is clear. And when it outgasses, it gets on the window. And so when we saw the video with the professor, and we thought, okay, thank goodness we didn't do it on the other chamber, because it would have gone everywhere.
Robert was aghast that his filters plugged up that much. It's unbelievable that that could happen. The only vacuum machine that I've ever used was to evacuate air conditioners on a car, right?
Oh, you've done that? Oh, nice. So you've had the understanding of what a vacuum... a lot of people have had the opportunity to use even that vacuum, huh?
Yeah, well, the idea, those machines only have to get down enough to get rid of the moisture, right?
Yeah, they go down to 5 pascals. That's 10 to the minus 1.
Yeah, 10 to the 1 torr. I mean, most of them are in mercury gauges and stuff like that, right? And it goes down, and basically the gauge on the thing just pulls it back. Like it goes all the way to the wall, and you think you pulled a perfect vacuum. Well, you're not even close.
Not even close, yeah.
And that's what people don't understand. They think that that is a vacuum. Well, no, it isn't.
That is actually considered reactive. For in our terms, you know, if you go with only the roughing pump and you're around 5 pascals, you are not in the high vacuum range, you're in the low vacuum range, and you actually do other processes there, because you do have a lot of atoms still remaining in the vacuum chamber, and you can actually go into the reactive kind of processing, you know, where you use the atoms inside to do some work, you know, to either do some nitrogen going into producing silicon nitride, or, you know, gallium nitride, or whatever. You know, if you want to make compound semiconductors, you sometimes use the reactive atmosphere, you know, the reactive atoms. What we do is we first wash it. We pull a vacuum, so all the air, which is composed of nitrogen and oxygen primarily, and a bit of argon, gets outside, emptied. You know, all the air gets emptied. Then the remaining molecules are air, but we backfill it with nitrogen, for example, okay? So we fill it with nitrogen and pull a vacuum again. So now the remaining atoms are nitrogen.
You're controlling the environment in which you're going to do the experiment.
Yeah. Normally you have a bit of a leak in the vacuum to supply gas that you're supplying. You have small parts per whatever you're measuring is, you know, some small parts entering, because it's reactive. Normally, you know, when you're using a gas to get incorporated in a film or whatever, it gets used up, so you have a small leak of that gas into the chamber. So from one side, your vacuum is pulling, and from the other side, you're leaking, you know, a bit of gas, because it gets used up in the process. When you have to supply a small amount, you know, you use those vacuums for that thing. To use also the gas, you have the residual gas you have inside the vacuum chamber. You normally use it to build stuff out of that. You know, for example, silicon nitride or gallium nitride might be a solid, but its constituents is a solid and a gas. It's a gallium and nitrogen to make gallium nitride. The molecule, when you get them combined, is a molecule, it's a solid. To make it, you have to supply gallium from an infusion source, from boiling it, you're heating it, getting some atoms outside to make your film, and then you use also the nitrogen in your chamber. That's material sciences. It's all the optoelectronics and all the processes and all the nice technological stuff. It's what defines our technological part of the era. Once IBM succeeded in taking thin film making, being able to make a thin film out of silicon, The method at the time was called thin film deposition through cathode disintegration, because you disintegrate a cathode, all the positive atoms hit you, and you disintegrate something that gets spewed over and becomes a film. Okay, yeah. So they got that, and they named it sputtering. It's an official name. After that, we saw the first processors.